Hi, a very good morning to Dr. Udila. So today we are going to present heat transfer presentation about daily using air fryer and industrial using nuclear reactor. So my name is KEAN, matrix number 206019.
Hi, my name is KANG and my matrix number is 206988.
Yes, so I will proceed with the air fryer introduction. So air fryer, we can consider as a cooking utensil where it's commonly used in the kitchen, and it can be counted as a countertop appliance which allow to cook uh, food to become crispier and golden fried food without using a pot or a pan full of oil. So how do it work? So normally the air fryer circulate hot air rapidly through its interior. So a fan circulate the hot air around the food in a perforated basket or tray, and all of the surface area of the food are exposed to the hot air, and the food cooked to become crispier on all sides without having to be submerged in hot oil. So the air fryer use hot air. It doesn't use like oil to submerge the food to become crispier. So this air fryer is in advantage of giving the food crispier, but with the reduction of the oil usage. So next, I will explain about the heat transfer in the air fryer. So you can see at the CFD there's a fluid flow from the heat from the hot air giving inside the air fryer. So a heat element is beside the cooking chamber, radiates from a closed ridge directly to the food. And you can assume that the radiation heat penetrates deep under the food surface, and a fan near the heater pull the air upwards through the cooking chamber, creating a strong airflow while passing the heater. And the air is loaded with heat energy, so the air is transferred downwards through a double wall around the cooking chamber with the minimum loss of flow and heat energy. So at the bottom, you can see the air is guided by a special, we consider a starfish shape, and it allows the air guide from the bottom distribute heat evenly and direct the flow in a vertical direction at the bottom to the up to make the food more even. So the food itself help to distribute the heat over the content of the basket. Only the bottom of the basket is open to the air, so it has to pass over the food surface when it is transferred to the food. So the heat reach all of the part of the food even when it is piled up. The combination of the radiation from the top and convection from the bottom creates a heat transfer rate that's much higher that than a convection oven. Simultaneously heating from both sides, it eliminates the needs of the turn the food during the cooking process. So the air fryer shows the same result, cooking crispy food with the reduction of oil, and without the presence of oil, the cooking air is internally recirculate to keep the heat inside, but when the temperature rise, so does the an internal pressure rise. Therefore, an air fryer also has an exhaust system to control the internal pressure. And an air fryer has exhaust features that it can take out small amount of air to create a small under pressure, force the steam and the smoke to leave the cooking chamber only through the exhaust, where it is filtered before it released to the open air. So next is the calculation part. So as you can see in the calculation part, we assume that the diameter and length is 15 cm and 180 cm respectively, and the delta T is 200 degrees Celsius, and we at the firm temperature 200 delta, we have find the properties of the density, thermal conductivity, viscosity, and PR, and we sub it into the Nusselt number and Reynolds number equation, and we can see that the Reynolds number have 3,573, which we consider as a turbulent flow. So if this is a turbulent flow, we can use the Ditto-Spatter equation, which is Nu equals to 0.023 times Reynolds power of 0.8 PR times power 0.4, and this equation we sub in, we can have 83.76. So after that, we sub it into the heat transfer rate. We can find it has 70.87 watt per meter square. And after that, we want to find the Q. The Q is the multiple of the H times A equals to delta T, and we get 3030.75 watts. So that's all for the calculation of the air fryer.
Okay, thank you, Cole. Next, I will be explaining about the nuclear reactor. So first and foremost, the normal two types of nuclear reactor we can find in commercialized. One is pressurized water reactor field and boiling water reactor fields. These two is widely used in our daily life, and both is working similar to a heat sink where the heat generated from the nuclear reactor, in our case, the core of the reactor, will generate tons of heat, and the heats will be transmitted to the fuel rod, and then we transfer to the water. The heat generated here is quite a lot. I mean, a lot. And the heat will transfer to the water. And in our case, I will be more specific to the pressurized water reactor field. The water then will transfer to another chamber that has water in it. And why it's called pressurized water reactor field? Because for our reactor, it is submerged in a pressurized vessel. So it can avoid the water inside it, the water submerged the reactor to boil. The energy will transfer to another vessel, another chamber that has water and coil in it. So the energy will transfer there and heat up the water inside the another chamber that has water to create steam. And later we'll move the turbine or the dynamo to generate electricity. So whenever we think of nuclear, we always relate to three types of the heat transfer form, which is conduction, convection, and radiation. But in our case, only involve two types, which is convection and conduction. For conduction, where it's occur is around the reactor core and the fuel rods, where our reactive substance undergoing fission will emit tons of energy, and this energy will transfer through a form we call heat energy to the surrounding water. And from the fuel rod, here we can see the convection is undergoing, so the heat from the rod will transfer the water and later to the another chamber and steam and turbine. So next I will show a video that explain more detail about it. So here is a video. So first of all, as I said, here is a simple arrangement of the reactor itself, the nuclear reactor. So we have a reactor core. Here is the place where we have the most nuclear substances and undergoing fusion, and it will heat up the water here. And here we can see a pressurizer where keep the water submerging the reactor core. So the water will not boiling. Where the water is boiling under a steam generator, where the energy from the heat energy from the core reactor will transfer to the chamber here. You can see my mouse. Then the energy here will transfer to the coil here to boil the water inside here to create a steam. Then the steam here, will help to move the generator and create electricity. So next, also we have a condenser, and we are taking a lot of water from, for example, the sea. So we can use a condenser and transfer it back to the steam generator and continues the process again and again, so we can produce a tons of energy. So next, basically, heat transfer in all application is similar, and I will proceed with my calculation and my case study. So as I said, I will focus on pressurized water reactor field. So this is my configuration for my case study. I will using a fuel rod as a arrangement of 14 by 14. The total length of the fuel rod is 4 meters, and each fuel rod is around 1 centimeter in diameter. So this is my calculation. So there is few assumptions to be made. So first of all, we assume the power output of the reactor is around 1000 megawatt. So next, I need to calculate the power inside the field of each reactor. So 1000 megawatt is the total output, the total power output of the field rod. So I assuming the reactor core have 100 assembly of field. So each field will contribute 10 megawatt of power to the whole system. So next is to find the, of course, for the further calculation, I need to find the area. Here my area is 24.64 meters square, and a few assumption and few more assumptions are made. For the K is 5 watt over mk, and the difference of temperature I assuming to be 200 degrees Celsius or 473 Kelvin. Sorry for my mistake. Yeah. And the mass flow rate of the coolant is about 2000 kilo per second. And the CP, the specific heat of the coolant, is around 4000 joule per kilo Kelvin. And so to find the total heat transfer rate, you need to find the heat transfer rate for conduction and convection. In our situation, we need to find the conduction first, where the formula is K times A times difference of temperature over the length. So I will get the heat transfer rate for the conduction is around 14,568.4 watt. And the heat transfer rate for the convection is around 3,784 megawatt. Each is a huge number. So to find the total heat transfer rate, you need to add up both of them. So we will get around 3,000 and 3,784.01 megawatt. So this is from me. Thank you.
Thank you.
Okay, I think this is from us. Thank you for your time, Dr. Ujira. So see you.
Thank you, Dr.